What's up, everybody? Welcome to Earth Science. How are we doing? Today we're going to look at the history of plate tectonics, which may sound kind of silly to do since we've already done a whole bunch of plate tectonics. We've done a couple weeks of it, right? But I think having a little bit of context for what's going on here is good for this little lesson. So not only is it relevant to tectonics, but it's also a little story on how the process of science works. Bad grammar there. Don't worry about the process of ELA. So what's the process of science? Like, how does this work? How did we figure some of this out? So going through the history, this will help us unwrap some of that. So this dude named Alfred Wegener, made a few important observations. So he noticed some things about Earth and Earth's surface and started to put his thoughts together and came up with a theory called Continental Drifts. Which states that the continents at one time must have been all together, and then they started shifting around. And we'll say this in a minute here, but the classic thing that everybody notices is that South America and Africa kind of look like they fit together, and especially when you do it with the continental shelves, they really match up really well. So he had like a bunch of great ideas, a bunch of great observations, was getting closer to unwrapping how this whole thing works. And it looked correct, but he could not explain the mechanism for moving continents. Hold on. How was it, Mr. Wegner, that a whole entire South America is just going to go moving along the ocean floor? Can you explain that to me? Wegner couldn't, and therefore the theory never really was accepted. Okay, so what did he notice? Africa and South America, as we just mentioned, looks like they fit together. Which you could say, okay, great, but that could be coincidence. You know what I mean? That's not enough to lock it up. Is that good? Is that enough? No, not really. Also, another thing you noticed, looking at fossils, is that fossils on either side of those match. These animals lived in geographically small areas. And after that, the continents pulled apart. It wouldn't make sense that this little critter here would specifically live only in this part of South America and this part of Africa if they were always separate. That wouldn't make much sense. If they're together, it does make sense. Animals live in little small regions, and that's that. So by matching up all of these, not only then do the fossils match, but the shapes of the continents match, and other things. Is that still enough? Well, he notices other thing. Glacial striations. Now, not everybody did glaciers this year. But the idea of a striation, it's a pretty easy one. Around here, upstate New York, we had like a mile-thick sheet of ice. That's heavy. And if at the bottom of that mile-thick sheet of ice, there's boulders stuck in the bottom, as that goes like sliding and moving over top of the bedrock, those boulders are going to cut grooves into the bedrock. So striations are like just grooves, lines, scratches in bedrock. Grooves, scratches in bedrock from the weight of the overlying glacier, right? One of the things that they're very useful for is it's a no-brainer on telling geologists or anybody really which direction the ice was flowing. You can see these in Central Park in Manhattan today. You can see them. You can see them all over the place. There's some up in the Thousand Islands. So you go there, you go to Central Park, you see these scratches, and anybody could say, okay, well, that means that the ice was moving in this direction because the scratches move in that direction. So if we say, no, Wegner, you're totally wrong, all of the continents were always in exactly the same position they ever have been, then the pattern of striations does not really make any sense. Whereas if we put them together, then the pattern of striations does make a whole lot of sense. And I should throw out there a quick note. The Pleistocene glaciation that we talked about, for those of us that did glaciers or those that just are kind of aware that the glaciers created a whole bunch of features in upstate New York, that was about 10,000 years ago when that ended, when that ice melted. This glaciation would have been a much older ice age. So just in case that's rambling around your head, not a big deal, but just to keep confusion clear, the Pleistocene glaciation that really affected upstate New York would have been when the continents were all pretty much in their current positions. This very, very, very old one would have been back in the Pangea days. All right. So all of this, you managed to put together enough where it feels like on the surface, it's a pretty convincing case. So the idea is like, okay, great. That sounds good, Wegner. But how's that work? Like, how does South America, how are you going to convince me right now today? How are you going to give me a way that South America could just like move across the ocean floor? What are you saying to me? Wegner kind of knew that they did, but his idea of drifting continents, he couldn't come up with it. Couldn't be explained. He didn't have the tools. Didn't have the mapping tools that would eventually be developed that would help figure out what's going on here. So none of this would be explained until first Wegner died. But he was right, but he never really got to hear anybody say he was right. And he was right in a limited sense. His continental drift theory, I mean, you could say it's wrong because he had the idea that continents just drift. He had all the things there, but to get to like full-fledged plate tectonic theory that we now know is like happening, but that we have an unbelievable amount of observations to support it and measurements and processes that we've seen, to get to full tectonic plate theory, it wouldn't be until after he died. So second, we started scanning. The thing that really got us there, it was a woman, the last name was Tharp, I believe, and she should really be in these notes. She's not. We started scanning the ocean floor. Found out there's all kinds of cool stuff going on down there. The old thought was like continent down like a bathtub, just across and then back up. There was no reason to think that there was anything else going on down here. Turns out there's seamounts, there's this giant ridge system that we've been talking about, there's these continental shelves. It's a pretty interesting place with a lot happening. So, using that Tharp idea, Harry Hess, really, and I don't know if discovered, I guess we could argue here, but we won't get into the weeds too thick, the mid-ocean ridge. Or Tharp discovered it, and he kind of took the idea as the next step. And from here, he really came up with the full idea of plate tectonic theory, but mainly driven by sea floor spreading. Now, talked about this. If you haven't done these notes, then you shouldn't be doing this right now. Seafloor spreading is this idea right here. And this is already in your notes, or it should be. Otherwise, please stop right now, go back and do this in order. Seafloor spreading is this idea of a divergent oceanic plate boundary, where at these mid-ocean ridges, this plate goes this way, this plate goes this way. So now we've got a mechanism to say, okay, if the Americas are over here, Europe, Africa is over here. If this ocean floor is continually spreading open, that's why these continents are moving apart from each other. Not the continent itself just grinding along the seafloor, the seafloor itself opening up, and then in other places being destroyed. This is really what's going to drive what we now understand is like the modern theory of plate tectonics. Okay, there's always a spread. That plate's going that way, that plate's going that way, like two conveyor belts at the grocery store rolling away from each other. So yeah, at mid-ocean ridges, the plates diverge. That we should be comfortable with that by now. They're spreading apart. And brand new ocean crust is created. Day by day, somewhere along that mid-ocean ridge, like today, that's happening. Let's go to Google Earth. Oh, and my tectonic boundaries are still on. So that green line, the red are little transform faults that offset. You can't really have a straight line on a curved Earth, on a spherical Earth. You need these transform faults to offset it. So we got spreading, and then spreading, and that creates these red are like the transform faults that just kind of relieve the stress on that. Okay, so this whole entire thing, and you can see it even if I turn this off, you can still see the mid-ocean ridge, right? So at this place, new crust is created, and it slides outward, and it slides outward. Out towards the edges then would be the oldest ocean crust, which is about 200 million years old. Cool? So now we have our full plate tectonic theory. Wegner was essentially correct, but now Hess added the idea that the continents move because I don't think the grammar is correct here again. Ocean ridges opens up oceans. It doesn't sound right, but this is the correct term. If there shouldn't be an S there, no big deal. Mid-ocean ridges open up oceans, and the continental plates, since they're attached, move along with them. Okay. So we're not doing that down there. Let's do this, and then we're going to do a lab that deals with this. That's a kind of a bizarre concept in the lab, but it's going to be really, honestly, one of the easier labs you're going to do all year. Where you're just going to look at some of this mapping of the magnetism of the ocean floor. So since then, we've detected these patterns in the basalt. Now, the ocean floor is basalt. It's mafic igneous rock, basalt. So it cools very quickly when it hits that cold ocean floor and forms basalt, right? A fine-grained, extrusive igneous rock on the mafic end of the spectrum. And then spreads out. So what has been noticed is that what we can do is, being that mafic rock has iron in it, it has it's a record of Earth's magnetic field. Now, Earth's magnetic field, grab yourself a compass, the little needle points towards the magnetic North Pole, which is a little bit off of the geographic North Pole. And that's that, right? What we've noticed historically through time, going way, way, way back, again, this is geologic timescale, not human timescale, that Earth's magnetic pole wanders around a little bit. It's not always exactly where it is. That's actually happened in human history, where we've been able to see, it's like somewhere right over here now, we've been able to see that the pole has been slowly moving through time. Sometimes it strengthens and weakens. Sometimes it's a stronger field and a weaker field. And then sometimes, and this feels very weird, it completely flops over. In other words, if you had a compass, the north end of the compass would point down here. North and south magnetically, what those are, completely reverse. These magnetic polarity reversals. So we've detected these patterns in the basalt and the seafloor. Basalt is mafic, therefore contains Fe, which you guys could get from your reference table, which is iron, which in itself is magnetic, right? That can't be it. Magnetic. All right. Earth seafloor, therefore, it's like a running record. We've got 200 million years of seafloor in the Atlantic Ocean. This looks more like a Pacific situation. But if this crust right here, right at the ridge, is like 0 million years old because it formed very recently, some of it today, and then all the way towards the edges is at 200, we've got 200 million years of record of this happening. So Earth's seafloor records the history of these magnetic reversals. So it's kind of a heady idea. Again, and that's why the lab is going to feel a little abstract. It's going to look a little weird. See these crazy lines here? You're going to be doing something with those. And it might be a tiny touch too complicated, but at the end of the day, we're going to make it very simple in saying that this demonstrates one thing. And if you can get that one thing, job done. And you're going to get a 30 out of 30 on the lab, and it's going to be fast and easy. Through time, these have occurred many times. Each of these, man, I can't even spell that right. Each of these reversals is recorded in the basaltic. Cool. All right. So here's that one thing. What's the one thing you got to know for the lab? Is that as this spreads that way and that way, maybe you can spot it. If you had to describe the pattern on either side of this dotted line, it's a word that maybe you've used in art class. What would that one word be? I'm going to make this just a touch bigger. So there's brand new crust here, and then it spreads, and it spreads. So what's going on either side? And this is going to be the only answer that you're going to have to come up with. And I think there's maybe 4 questions in a row where this one word is really the key to all of those questions, and that is that there is a symmetry. All that right? How about that? There's a symmetry on one side to the other. This shows that there's an even spread from one side to the other. Sometimes that one side will go faster than others depending on the situation, but there's still a rough symmetry from one side to the other with these patterns of these magnetic anomalies. And again, magnetic anomaly things that might sound complicated and hard, but if you can just recognize really that there's a symmetrical pattern, it's like job done for what you need to do here in New York State Air Science. Okay. So that's the key to your next lab. We'll say it again when we get there. I'll do that in a separate video. What do you think? Do we got anything else to do here? I think we're probably good. Okay. I won't say like there wouldn't be a test where you got to come up with somebody's name and say Wegner or Hess or Tharp or any of that. It's more the big ideas here and the idea that this stuff could all be very big. The idea of symmetry and seafloor spreading, but that's really what is driving plate motion. All right. That's great. Keep it up, folks. Lab next. Good luck.